Pascal is currently director of the Knowledge Engineering Lab at the Department of Computer Science and Engineering at Wright State University in Ohio, USA. And he spent his previous academic career at Karlsruhe University and Dresden University. He is a co-author of the book Foundations of Semantic Web, and on this subject he gave a huge number of invited talks in many conferences and events. The talk he is going to do today is about the recent advances concerning own and rules, and I think we think that this subject is very interesting for all of us, so I asked Pascal to come here. We are a bit earlier rather than a bit later, so we can have time to switch. Thank you.
Thank you. Do I need to use the microphone? Yeah, do I need to use the microphone?
Yes, please.
Okay, then I'll try. Yeah, let's see. I'll probably try to be stationary. In case I forget to speak into the microphone, please remind me. So thank you very much for the invitation. I'm very happy to be here. This is my first time in Istanbul. It's actually my first time in Turkey. I'm enjoying the place immensely. Very happy about that. It's not my first time at ICLP though. I've been in ICLP once before. That was when I was just starting as a PhD student back in 1999 in Las Cruces, long time ago. I have not been in ICLP since. When I looked at the papers and the authors of the papers of this year's conference, and I noticed that I know a lot of people by name, but I can't associate faces with them. So this is a very good opportunity for me to probably connect some faces with names and get to know some of you personally, knowing you only from papers. So I'll be talking about recent advances concerning Alvin rules. Owl being, of course, the web ontology language, recommended standard by the World Wide Web Consortium. Since about 2004, I've been embarking on semantic web research primarily. I've written a textbook, which is co-authored a textbook, which is very well received, and a copy of it should be going around in the room today. Just this year, a Chinese version came out, and I hope all the Chinese on that slide is correct, because I can't read it, certainly. And there's also some copies of the Semantic Web Journal floating around, which is now a 4-year-old. We're going into year 5, I believe, next year. Which is still a relatively new journal, which has been having a very good trajectory. One thing I remember from 1999 was that back then there was a big discussion in the community, a big fuzz in the community about setting up TPLP, and the whole editorial board of the Journal of Logic Programming resigning from that editorial board and going over to TPLP, essentially to say, well, we have our own ideas how these things should be done, and we don't let certain things be dictated by the publishers. We're very happy about the publishing house we're working with, iOS Press. So, for example, we have all the camera-ready versions publicly available on the journal homepage. And they also were very positive about some innovations to the review process which we introduced. So, for example, we do transparent reviewing. Reviews are signed by name. was partly an experiment that it actually worked out extremely well. But that would be for a different talk and not for this one. So if you're interested in that, let us know. I am at the Noesis Center, which is in Ohio, the Ohio Center of Excellence in Knowledge-Enabled Compute, Dayton, Ohio. I have a lab with about 10 students, funding mainly from NSF and from some other sources. And I'll stop the advertising now and come to the things I really want to talk about today. So, semantic web. I'm not going to really talk in detail about semantic web as a vision, as a picture as a whole. Partly because I'm just happy that I have an opportunity to speak in front of people who actually know something about logic, which is not always the case. So if I don't have that, then I usually largely ignore that part of my work and focus more on things which are a little bit closer to, say, well, the non-logical aspects, like data alignment, ontology merging, conceptual modeling, which I also do. Today I'll be talking about some of the logical aspects we've been working on. And what you see here is what some people call the semantic web technology stack. Essentially, the World Wide Web Consortium, which you might know is the standardization body for all things concerning World Wide Web, so they standardize HTML, XML, these kind of things. They have developed some standards which relate to the semantic web effort. And some of these are mentioned here on the slide. So what is the semantic web, and why does this have anything to do with logic? Well, in a nutshell, and really just in a nutshell, the key idea behind the semantic web is to make content on the web machine accessible, machine processable for intelligent systems applications of all kinds. So key aspects we have to deal with have to do with data integration, information merging, search, of course, and all methods you can find out there in computer science are fine for pursuing this purpose. You will notice that this links very well, for example, to the current big data hype, which is coming up. Because essentially, well, there's enormous amounts of data out there on the semantic web, and there's more coming, and people are already talking about sensor networks, and so on. And you have similar problems. It's about data integration, about data merging, about doing things automatically, which currently we essentially only know how to do manually by, say, data curation or manual database schema mapping, etc. So you want to do that web scale. And that's the big vision. And of course, in the 10 to 15 years that researchers have been working on this big vision, certain things have materialized as, say, well, the approaches people try to follow when doing that. Now, whether these are really the best paths of doing that, that's a different question. But you know how research works. Just move somewhere. And we have to see how we can advance the state of the art from where we are. Now, what comes into the picture here is knowledge representation, of course. Well, I say of course, other people would say, well, it's not so much of course, but for me it's of course. You want to integrate information. So part of the question of the semantic web endeavor is, what is the best way to represent information, to represent the content of information, the knowledge on the web? And, well, you here being logic programming researchers, you would probably also say, well, okay, it's at least worth an attempt to try logic-based formalisms, looking into knowledge representation formalisms for doing that, for attempting to do. And this is what is happening. So this is one of the lines which is being pursued. And some of the standards developed by the World Wide Web Consortium for supporting this endeavor are essentially webized versions of knowledge representation languages. So this is where we are. And by ignoring most of this picture, just those two pillars here. There is one thing here, which is the web ontology language OWL, which is based on description logics. And this is going to be the starting point where I talk today about. So you'll get a little bit of an introduction there as well. And also look at this pillar here. This is rules, the rule interchange format RIF. I'm not going to talk much about RIF also because there's at least one person here in the room, named Michael Kiefer, who would be much more qualified to talk about RIF, of course, because he's been one of the drivers of this standard. But let me just give it in a nutshell. Now, ignoring syntax issues, of course, which are important if you when we want to work on the web and want to exchange information. Looking at the logical content, there's several dialects, parts of the RIF standard, and one of them essentially corresponds to data log, and one of them essentially corresponds to logic programming. So this is part of the world and has been part of the semantic web endeavor since the beginning. And this standard was installed in 2009. The web ontology language OWL is based on description logics. And while I was not around when that decision was made, that was made in, well, the early days of the last decade. The standard was actually, became a recommended standard in 2004. I hear that the discussions which paradigm to adopt as the ontology language for the semantic web, that was a rather controversial issue. And I mean, of course, these things easily become political. In the end, description logics kind of made it, gave them a big boost. But I would say there would have been at least as many good reasons for adopting a rule-based approach as that, and then the semantic web will probably look a little bit differently today. So that's the situation. Now what I'm going to do today is talk about how OWL and description logics in that sense relate to the rules paradigm, how they relate to it and how they don't, and what has been happening there in that area recently. So I will first talk a little bit about description logics, and then investigate which rules can we express in OWL, which ways can we find to push this, to do even more, and then also talk a little bit about recent algorithmizations, and hopefully I also have time to talk about a little bit about non-monotonicity in that context. So the web ontology language OWL. It's a recommendation by the World Web Consortium since 2004. There was a revision called OWL2 which was installed in 2009. The revision was really an extension of what we had previously, though I think a lot of things are much better. It is based on description logics. Now, if you don't know description logics, then let me give it to you in a nutshell. Description logics are essentially fragments of first-order predicate logics. So that in particular means that we are adhering to a first-order predicate logic semantics. So no Herbert semantics or anything like that. No closed world. We're really talking first-order predicate logic with all the positive and negative sides of doing it. Furthermore, and this is a key piece for description logic research and development, we're talking about decidable fragments. And if you don't know about description logics, then, well, what decidable fragments of first-order predicate logic do you know, right? And then you might come up with propositional logic. Okay? You may come up with data log. That's a rule paradigm. So what else would there be? I mean, how much can you really do anything with a decidable logic? And why would this be important? I mean, you're logic programming people, so you might be wondering, but is this really important? And that's a good question, and that's actually also controversial in the semantic web community. However, focusing on decidable fragments has obviously been helpful for the description logic community, probably also because, well, it was a different angle on knowledge representation. So that helped. The arguments which could be put forward, why it's interesting to look at decidable fragments would be, well, some people claim that these usually are easier or better to implement efficiently. I don't know whether that's true really, but that's what some people claim. And when you have decidable languages, then that also means you can do a complexity analysis on those, which might be a kind of a priori guidance, which might help you, to understand what kind of features do you want to kind of keep the complexity low, because those might be better for applications and easier to deal with. Now, that's part of the reality. So if you want to write a description logic paper, it should usually have a complexity analysis. Okay, it's just what the people from that community expect. So, in a nutshell, description logics. Description logics, so it's a family of logics. It's not just one logic, it's a family of logic, which have different complexities, of course. Description logics have three different basic entities you can talk about. And they easily correspond to things we know from predicate logic. So this is how I'm going to explain description logics to you, which I can do with you because you know about logic. You can do that with a different audience, of course. So on the one hand, we have classes, also called concepts sometimes. And these really correspond to unary predicates. You will see that for the description logic world, there's actually a variable-free notation. So they don't appear on the left-hand side, but they really correspond to unary predicates as you're used to. There's roles, sometimes called properties. I'll use both interchangeably, which really correspond to binary predicates. And there are so-called individuals, which are really just constants as you're used from the logic. So we don't have tertiary predicates or anything. We only have unary and binary, and this all has to do with the fact that we want to obtain a decidable language. Some constructors. Constructors, in particular, for complex class expressions. If C is a class and D is a class, then the conjunction of C and D is a class, of course. So this expression on the left, I like to do this with these squared connectives, corresponds to C of x and D of x. And there is a constructor which is called the existential restriction. And now things start getting a little bit more interesting, and also a little bit more weird if you haven't seen that before. This looks like this, where R is a role, binary predicate, and C is a class, and you put the existential before the role. And if you translate that into first order predicate logic, then it just means this here. So this is a class, it's a complex class, it's the class of all x's, such that there exists a y which is related to x using the binary predicate R, and y additionally is in C. Okay. You can trace this back to so-called guarded logics. And this restricted use of the existential, so this is the only way you are allowed to use the existential, is something which is necessary to retain decidability of these logics. Now once you have class expressions, and this is the very minimalistic description logic, there will be more constructors later. If you have such complex class expressions, you can now nest these, of course. Then you can talk about class inclusion. C is a subclass of D, or C is equivalent to D, which just translates like this. And think of these things on the right-hand side always in a first-order predicate logic semantic. So this is the reading we should give it. Additionally, look at the following. This was a relatively late introduction, but which is going to help us a lot for discussion we're having here. So-called role chains. You use a concatenation symbol. Here, R1 to Rn are roles. R is also a role, so this is not class inclusion, this is role inclusion. And this essentially translates to this here. This is a role chain. X to x1, x1 to x2, and so on up to xn plus 1 implies R of x, xn plus 1. This is a role chain. And you're allowed to use this only in this fashion. Okay? Only as such a chain of x's, and this is the first, this is the last in the chain. Now this looks very restrictive. In particular, if you look at these things from a logic programming or data log perspective, I mean, so what's to that? What is old? What is new? Well, this is essentially a rule, right? Well, here you can use to make conjunctions, but for example, you have seemingly no way to mix unary and binary predicates conjunctively. You have a very severe restrictions on the use of the variables in the role chain, so this isn't all useful. Now, on the other hand, you have the existential, which in particular you can have on the right-hand side of a class inclusion. Now, this is something not usually available in logic programming languages, but there's something different happening here. And you might already notice, oh, this looks a little bit like existential rules, like data log plus minus. And I know there's at least 2 talks here relating to this. Yes, the logic which I'm presenting here is very closely related to those, although different. Okay, let's keep going here. So this would be a little example for the very minimal logic which I've right now started to introduce. Tie-dish is a class, so this first statement would say if something is a tie-dish, then it contains something which is a nut. If you're not allergic and you eat something which is a nut, then you're unhappy. And if x eats y and y contains z, then x in fact eats z. So that kind of makes sense. This would be a little knowledge base. Now, the existential can be used to infer the existence of things we don't have names for. We're talking about first order logic semantics. Okay? So we're not talking Herbert semantics where we only have the constants which are in the knowledge base. And you might already notice or might already suspect that this is one of the things which actually we have to look at when we talk about decidability of these languages. Now let's introduce a further constructor, so-called inverse roles. This looks very innocent. The role R equivalent to S minus, which essentially just means you exchange the two predicates. Now, once you do that, in addition to the things we've just talked about, which really wasn't much, role chains, conjunction for classes, and the existential restriction, plus inverse roles, then this logic is already undecided. This logic is already undecided. Now, description logic, people care about that. Okay? Now, you can't really say much here, okay? But the logic is already undecidable. In a nutshell, the reason why this is undecidable has to do with the following. The intersection of context-free grammars, well, finding out or the equivalence of two context-free grammars is an undecidable problem. You can use the existentials and the role chains to essentially construct grammar, to mimic a grammar. And then you use the inverse to mimic an inverse grammar, okay, going backwards on the context-free grammar. And then what you do is you essentially try to find out whether you can construct something and then go backwards in the other language and kind of come back at the empty string. So you can use this minimalistic logic to encode an undecidable problem. So this is why the logic can be understood to be undecidable. So this logic would be called ELRI. These description logic people always use these kind of symbols, each of which means something. E in that case indicates the existential. EL would indicate existential conjunction. R is role chains. I is the inverse. So all these strange names for their logics, they actually have a meaning, and you can read out essentially what the logic is. So this is undecidable, which is something they don't want. So what would be remedies here to retain decidability? Well, there are several ways how to do this. And again, notice that this is very close to existential rules. Now, the way how the existential rules people, the data log plus minus people, attain decidability is very different from the methods I'm going to talk about here. I believe that, and I'm not an expert here, other people need to talk about this, but I believe one of the main things they're looking at is some kind of preventing acyclicity through the rules. Plus notions of safeness, as they call it. Anyway, that's for somebody else to talk about, I guess. So, how can we retain decidability? First obvious solution is disallow the existential. Okay? What we get if we do that, we essentially get a fragment of data log. From a data log perspective, a very weird fragment of data log, of course, because you're very restricted in the use of the variables in the rule bodies, etc. However, if you go this route, disallow the existential and then add some more, a little bit more description logic, which you can add without losing complexity, mainly, then this essentially leads to one of the substandards of the web ontology language, namely OWL-RL for rule language. So this is the idea behind it. And this logic is tractable. It's tractable because it's translatable into data log, and because you have the binary predicates and the specific buildup of the sentences, you can restrict to that there's a global bound on the number of variables you need per rule. So that and that then gives you polynomiality data. So this would be the first way to go, and this is one part of the standard. Now, another way to go would be to disallow inverse roles. So you're not allowed to swap arguments. And yes, that works as well. If you go this route, then with some additions on top, again, this leads to another substandard of the web ontology language, which is called OWL. And this is very much akin in spirit to existential rules. This is a tractable polynomial time language again. And this, in particular due to the existential, is very popular, for example, in the biomedical domain. They like to have an existential for modeling, for saying things like an arm has a hand, although we might not have the hand in the database. Now, a third option of retaining decidability would be to understand, well, we could restrict the recursion in the role chains. So if we have several role chains which recursively connect to each other, now remember the reason for undecidability, context-free grammar definition, then we might be able to restrict the recursion here somehow to retain decidability. And again, the idea how to do that comes from formal languages. Namely, well, if it's about intersecting context-free grammars, which is undecidable, then let's just make sure that we cannot model context-free grammars, but we can only model regular grammars. And then we don't have a problem with respect to decidability. Okay? So one way is to put restrictions on the use of role chains, which are actually become known as regularity restrictions because they come from this idea of restricting to regular languages. Essentially, that means that, well, you can do end recursion and front recursion, but you cannot do the recursion in the middle of a role chain. That's the basic idea here. Of course, you need to spell this out formally, but I believe that intuition suffices here. If you go that route, then yes, that works, but it's not tractable. So it's not tractable to begin with. It's still decidable, and you can add further constructors, which I'll also talk about in a minute. And this essentially leads to currently to the description logic SROIC, which is a very expressive description logic, which is the OWL-DL part of the OWL stack. DL standing for description logic. We are currently, one of my students, is currently working on trying to lift this restriction, trying to find a fourth method how to do that. But I'm not ready to present that yet. So, but of course, there's more work which can be done. So, further essential description logic constructors. The following can be used in OWL, which is the one which is close to existential rules, and the logic still remains tractable. We don't use polynomial time complexity. The first is the so-called self-construct. And I really don't like this notation because it's not an existential. Okay? It looks a little bit like it here, but it isn't. This construct, C, is a subclass of exists r.self. The self is not a class. Okay? This is just a piece of syntax for this compound. And the easiest way to understand it is just translate it into predicate logic. This is really C of x implies r of xx. And you can obviously also do the inclusion in the other direction, which allows you to model stuff like a narcissist is somebody who loves himself and stuff like that. However, as we will see in a minute, this is in particular can be used for typecasting. So you can use that to convert classes into rules and rules into classes, which you might ask, so what the heck, why do you want to do that? Well, we want to do that because the use of classes and the rules of roles is very restricted in this description logic syntax. So in a sense, we're doing this to recover from something which was a problem in the first place. Okay? The key idea always being retaining decidability. Now another constructor which you can use is so-called nominals. A nominal, and the syntax we use is this here, curly brackets, and a constant written in the curly bracket. This is the definition of a class by naming the extension of the class. So this is the class containing exactly and only the constant a, the individual a. And things we can express if we have this constructor is of a. We can say C is a subclass of such a class, which actually introduces a type of equality into the logic. So that's also no problem. C of x implies x equals a. And also we can model equality of constants. Now notice first order logic semantics, meaning we don't have a unique name assumption. Okay? So it's completely possible that two things are actually equal, although they have different names. Think of two URIs. In fact, if you look at the web versions here, and I'm giving you the logical substrate only, if you look at the web versions, then the constants, of course, are URIs. So they stand for web resources. And certainly your homepage can have two different names. Okay? So you don't want a unique name assumption. To give an example for a little bit more complex axiom, A intersected with exists R dot B, the nominal B, then can be translated in that case into the rule A of x and R of xb implies C of x. Interpret under first order logic semantics. So well, seems like we can say a lot of these things in rules. Okay? Which things can we not say in rules? Well, the existential might be a problem. We'll come to that in a minute. Further essential, the L constructors. These are ones which are not available in these tractable logics, AuliL, but they are available in Sroig and AuliL, the expressive description logic. Class negation, which is a first order logic negation. It's really a true first order logic predicate logic negation. Once you have that in conjunction, you obviously also have a disjunction, and you get a universal restriction, which is really just, well, you know, you can get the universal with the existential and the negation, just in the ways you're used to. And there are some more, of course. Okay? So as soon as you have a first order predicate logic negation, you're stepping out of the kind of traditional logic programming framework, of course. So, given this, relating rules to OWL and the other way around. So some things are already very obvious from what we've been talking about. An axiom like class A included in B becomes an easy rule. Likewise for role inclusion. This is just a role change with only one predicate. So these are very straightforward. Even more complex expressions, like say nested existentials, well, that's easy. Rxy, syz, b of z implies c of x. Now notice there is always this main variable here on the left-hand side, which also appears on the right-hand side. This is the main thing we're talking about, because this is a class expression. Okay? And the x's are in this class. And all these x's are then also in C. So this is the kind of restriction we have when we talk about these. This here becomes a fact that A equals B, for example. We can do this here. This is the bottom class. Just think of it as C intersected not C. Okay? So it's empty. It's the empty class, which would correspond to something like an integrity constraint on the logic programming side. And of course, the role chains, we talked about those already, are just these expressions coming from the binary predicates. Okay. And then you, of course, can use all the tricks you have for converting first order logic formulas into Horn clauses, right? So if you have a disjunction negation on the right, you can actually move it to the left. The universal on the right actually becomes an existential on the left. You know all these tricks. You can do some Lloyd Topering as much as you want. Okay, so essentially, description logic rule, you want to convert it in the description logic axiom, you want to convert it into a logic program, or in data log expression without going through formalization. Then what you do is you translate the first order logic and you try to form it into Horn clause. If it works, then you have it. Okay, so this is relatively straightforward. Now, this is more tricky. Okay? Now, this is a rule, this is a Horn clause. Can we express this in description logics? Now, there's a problem here, of course, because on the left-hand side, we have classes. On the right-hand side, we have a binary predicate. Okay? Now, our description logic axioms allow us to relate classes to classes and binary predicates to binary predicates. So we need to bridge this somehow. And that was a few years ago when we wrote this paper, which actually has elephant and mouse in the title, because that was something which people only started to become aware of at that time. That you can indeed model that, because you can use the self for typecasting, as I mentioned earlier. Okay? If you have a concept A, you introduce a new binary predicate RA, a new role, and make the statement A is identical to exists RA.self, and that essentially means you typecast the unary A predicate into the binary R predicate. You can do this for both the class elephant and the class mouse, introducing those two roles, and then use another constructor, or another entity which I haven't mentioned yet, namely the universal role, which is the role which connects everything to everything. So it's the Cartesian product, really, which is the extension of this. Make this role chain and make usually bigger than on the right hand side, and then you have modeled it. This trick is, we call it roleification, because we roleify the concepts. Okay, and then you can just look at all types of rules which mix unary and binary predicates, in the bodies and use this rollification trick to translate them. Should be a more complex example. Oh yeah, this is a different. Okay, so one example here. Woman X and married to XY and man of Y has a husband XY. Okay, if we want to express that in description logics, then we rollify woman, we rollify man, make this roll chain and say this is a subrole of has husband. Okay, there's a problem. Right? There's a problem. And the problem is that if you want to model a knowledge base using these notions, you may just want to state something like has husband is a subclass of married to, or is a subrole of married to. However, if you do this in conjunction with this expression, then you actually get a recursive dependency between has husband and married to, which violates the regularity restrictions. Okay? So in fact, you're not allowed to make this statement at the same time as this statement. Now this is rather unintuitive. Okay? And at this stage, you might wonder, so why not just use rules? I mean, that's easy. Okay. So in any case, that's a problem, of course. That's a problem. I believe that's a problem a lot of people on the practical side of semantics are not aware of because they're struggling with all this logic. But this is a problem, of course. Yeah? That is also one of the starting points for us to look into, well, can we actually unfreeze this regularity restriction? Well, we already know that if we don't have inverse, we're fine. Okay, we're still tractable. But if we have inverses, then there's some work to do here, of course. So, in some cases, like for example for this rule, you may have to rollify a complex class expression to do it, to translate. The general question which all this begs is, so under anecdotal evidence, can we somehow put our hand on now which rules exactly can you translate and which can you not translate? And the answer is here. The answer is that the key thing is that on the description logic side, we do not explicitly have variables. So the expressions which we have for making classes, they're always rooted in one variable, and then from there it's a kind of tree-shaped expression which goes out from there. So what we do to understand whether we can translate a rule into description logics, we take the rule like this here, look at the binary predicates only, and make a dependency graph of the variables. Okay, well, it's not a dependency graph really. We make a graph of the variables where the edges are the roles. So R1 connects X to Y, and R2 connects Y to Z, and so on. And afterwards, we actually ignore these loops. So we forget those loops. And if what we have here is a tree, okay, with a root from which we can really reach everything, but reach everything in only one way, plus the root variable is the variable appearing here, then yes, we can translate that into description logics. And the corresponding description logic expression would look like this here. Now think of this rendered in XML. Okay, it's completely unreadable. I mean, it's almost unreadable in description logic syntax, even if you're a description logic researcher. Okay? So what I in fact do, I mean, since we're working on OWL and rules, if I do ontology modeling, I usually write down my axioms as rules and then convert them. Okay? And that says something. I don't know about other description logic people, how they do it, but that's how I do it. Because rules are just more intuitive for the modeling. It's much easier not to make mistakes. Okay, now if you have something like this here, now the only thing which happens here is that some of the variables were swapped. Okay, so the arrow goes in the other direction, meaning X is no longer the root here of this tree. Okay, what can we do in this case? Well, of course, if we have the inverse role constructor, then we're fine, because with the inverse role constructor, we can just swap the arrows. So that's okay. We just have to keep in mind that we may run into this undecidability problem because our set of role chains needs to be regular to retain decidability. So we need tree-shaped bodies of the rules. We need that the first argument of the conclusion is the root. And then we can do the translation. And we really need to look only at variables, because if we have a constant in this graph, then we can just as well duplicate the constant, because the constant becomes a nominal which we can just state twice in data. So that's fine. We don't have variables, but we can talk about constants. Okay? If we have in the conclusion a binary predicate, then the idea is exactly the same. We make our little graph here, dependency, so I duplicated the A already. We could also just remove those nodes. We have a binary predicate here, and in fact it's the very same condition which holds, it's just the method for translating is different because we need to do typecasting. So we do the typecasting, possibly on some complex atoms. So this is rolified. This is the class which is rolified into R1. This is the class which is rolified into R2, and then we use a roll check. Okay. So same picture, just that the first argument of the conclusion needs to be the root of the tree which we have on the body side, and then we can translate it. So that works rather neatly. Now, rules don't always look like this, of course. Rules don't always have tree-shaped bodies. However, it's rather interesting to see that very often they do. And if you have practical examples of rules which were used for conceptual modeling, which don't have a tree shape, please let me know. Okay, I'm always looking for examples. Because it's a little bit of a kind of convincing thing for the description logic community to say, yeah, we need those others. But not everybody thinks it's obvious. So this here would be a rule. Which talks about a situation where a conflicting review assignment occurs. Now, the exact content of the rule doesn't really matter that much. If you look at the structure in terms of graph, then what you get is this picture. Okay? So this is certainly not a tree. Yeah, it's far away from being a tree. So from what we've just looked at, we cannot translate this into description logics. This is a rule we cannot translate into traditional description. However, if just y and z were constants rather than variables, so in this case, specific people and a specific person, a specific author, and a specific conference in that example, then we could actually do that. Now, it may be reasonable to say that if I want to check whether there's a conflicting review assignment for a conference, then I actually know which conference I'm talking about. And I also know the set of authors. It's probably not one, but it's a finite set, and I know who they are. So what I could do is, I could just ground this rule with respect to those two variables, which are the culprits, and destroy my tree structure. Okay. Now, if I do this over several conferences, then that would mean the grounding is going to probably become rather large. Okay, say 100 times 100 or something like this. If I have a third variable which screws up the loop, then I have 100 times to the power of 3, so the thing grows rather largely. But yes, that would work. So if x and y were constants, then I could translate this, and the translation, again, is a little bit complicated, but we know now we can do it because we get a tree structure. Okay. So let's drive on this. So writing down all these 100 or 10,000 rules, because I have to ground this to express it, is not very convenient, of course, right? So let's do the following. Let's just say we have a type of variable, in this case the y and z, which are not first order predicate logic variables, but which are what we call safe variables, DL safe variables. And we change the semantics of the whole thing in such a way that these variables bind only to known constants, to known individuals in the knowledge base. Sounds familiar, right? In a sense, if you have function-free logic programming, you use the Herbert semantics, then that's kind of what you do, right? Because you don't have an existential which might create new stuff you have to take into account. So you only have the known constants anyway. So we're staying true to the rule paradigm, in a sense, yeah, from this perspective. So let's introduce those two variables which can bind only to known constants, which then means we can in principle ground this rule with respect to only those two variables, not the others, because right, open world, existential, and so on, but with respect to those two variables, get a lot of rules, but yes, we can in principle encode this in our description logic then. So this works. And then, of course, on the description logic side, we would like to be a little bit smarter and not write these 10,000 axioms. So what we do is we extend the description logic paradigm by reintroducing something they've thrown out early on in the process, namely variables. It's just that they are not first-order logic variables, they're DL-safe variables. And we tend to call them nominal schemas or nominal variables. So this is just what we had earlier. This is just the translation of this if this and this were constants. Okay? Using the tricks we had earlier. However, in this axiom, you notice these nominals which have the y and the z in here, and rather than understanding them as constants now, they are in fact variable, they're nominal variables, meaning they can bind to individuals which are known by name in the knowledge base. Okay, and then of course, if you want, you can ground this with respect to y and z and get a lot of traditional description logic axioms. So this is really syntactic sugar. It's very powerful syntactic sugar. So if we do that, what do we get? Well, of course, we retain decidability because we can just rewrite it. It's syntactic sugar. Now, what happens with respect to complexity? Now, interestingly, complexity is retained. Okay? Now, this is not trivial because if you take new axioms which have more nominal schemas, then with the number of nominal schemas per axiom, you actually get an exponential development. Okay? In that case. And the underlying logics are exponential as well, so you may get something like a double exponential on top. However, it's not happening. I mean, these logics, the expressive logics, they are really double exponential, non-deterministic and stuff like that. There's a lot of space. So you can fold it back into the same complexity class in many of these cases. The reason is essentially that some of these complexity results come from known analysis on what's called as the two-variable fragment of predicate logic. Because often you can translate this description logic into this two-variable fragment, and that's still the same. Okay. A naive implementation is straightforward. Replace every axiom with nominal schemas by a set of L2 axioms obtained from grounding nominal schemas. That's a naive approach. Okay, full grounding. If you do that, then of course this is not going to work in terms of real-life reasoning. Okay, because the knowledge base is just going to blow up tremendously. What do we have? We have, in a sense, a powerful macro, syntactic sugar, but even more than that, we have a conceptual bridge to rule formalisms. Okay? And in particular, and that I don't have the time to go into detail here, in particular, what you can do with this construct now, if you do the encoding correctly, we can actually capture n-ary data log. And we can capture data log not only with unary and binary predicates, but with n-ary predicates, and translate that into this paradigm, just by introducing the nominal schemas. So this is what happens. Okay, of course, after we did that, and I have to say that this, of course, didn't fall from the sky. There was a development which led towards these DL-safe variables, which took a couple of years with several steps in between. Now, when we finally arrived there, then one of the questions was, of course, so how can we now find smart algorithmizations for this? And we tried many of the methods which are out there for making description logic reasoners, which include use of order resolution techniques, which sometimes leads to very powerful reasoner paradigms. We tried Tableau algorithms, of course, which is the primary traditional way of doing expressive description logic. An algorithm on paper where we said, now we don't really want to implement it. It doesn't look like it's going to run. So, but however, there's better news on the next few slides. First thing we did, though, just to have a baseline, was to look what happens if you go through full grounding. And I mean, this is no surprise, of course. If you have very small size knowledge bases, say under 1,000 class names, with say 100 individuals or so, then if you have 2 different nominal schemas per axiom, then the times already start becoming rather ridiculous. And if you have 3 different nominal schemas, then you start getting out of memory very easily. Simply because you're exponentially blowing up in the number of nominal schemas per axiom. So obviously this is not working, but that was our baseline, which we wanted to get. Now, looking at tableau algorithm, one of the primary approaches for description logic reasoning, the straightforward idea here is to do delayed grounding. So you take your tableau rules, you add a grounding rule which grounds only if necessary. Because in a tableau-based approach, the problem is if you have a nominal schema appearing in several places in the axiom, then you cannot just send that into different tableau branches without further ado. Okay, so you may have to do the grounding sometimes before you distribute, or use some good tabling methods for keeping the overview. In any case, we did that. We looked at the algorithm and kind of were at a loss in how to improve it. We didn't even implement. And then the good thing is that this summer, from Ulm, Bertie Glim is leading a group there. They made a paper at ICLP this year, which talks about implementing nominal schemas in a tableau algorithm. And they used an optimization, which is known as absorption technique. Now, without going into detail, essentially what they do is to do a type of upfront rewriting of the knowledge base, which, when running a tableau algorithm, removes non-deterministic aspects. So it removes the need for backtracking in the algorithm. And this is a relatively old technique which is just adopted to nominal schemas. The result of this, obviously done by people who really know how to software engineer a reasoner, are rather good, right? They used a very restricted form of nominal schemas for the testing of the efficiency of their implementation. They use this restricted form, which is known as the L-safe rules, because in this restricted variant, other reasoners can handle the same logic. Hermit is known as a very powerful reasoner, which can do that, and Pellet, of course, is one of the primary description logic reasoners. So they could make a direct comparison between the methods they use for dealing with the L-safe rules with the method they have developed. Hermit, for example, uses something called hypertableaus, which is a mix of resolution-based and tableau-based methods for dealing with this type of rules which only contain the L-safe variables. So this is a different approach. And you notice Hermit is pretty good in terms of runtime compared to Pellet, which uses a much more naive approach to deal with this type of rules. However, this new implementation using absorption, I mean, it just trashes them, right? So we're talking here, Hermit, 30 minutes, we're talking here half a minute, okay? We're talking here 1.4 minutes, we're talking here 7 seconds, okay? So this is really cool, it's really nice. And this is a rather unexpected twist, okay? What we did with these nominal schemas, we essentially found a way of generalizing a form of rules with only the L-safe variables, by saying not all variables have to be the L-safe. We introduced essentially just a convenient syntax, which if you look at it in hindsight is more or less straightforward, okay? Reintroducing a form of variable on the description logic side. And now what they do here is they use this idea, actually not for obtaining more expressive power, they use this for developing a more efficient implementation of a paradigm which was already there before. So this is rather cool, right? This is rather nice. So I'm very happy they did that. What we're currently focusing on is looking at a tractable fragment of this logic. So we're looking at this EL type of thing extended with nominal schemas. You have to be a little bit careful that you don't lose tractability, but it's possible. So there's also a polynomial time fragment. We based our algorithm on some work presented by Markus Kröch at GILIA 2010. What he did there was he presented an algorithm based on a transformation to data log. So although there are extensions in this logic, you can translate this into data log and do data log reasoning to solve, to do reasoning over your logic. And we essentially use this algorithm, made an extension which can deal with nominal schemas. Regretfully, well, as usual, we were a little bit of a hurry doing finalizing the stuff. So we just took a reasoner off the shelf, which was a research prototype, which we could easily program against, so it's not very efficient. So don't look at the absolute times on this chart, but look at the development of the runtime if we increase the number of axioms per nominal schema. And remember, the naive grounding essentially gave up at 3 nominal schemas, and at 2 nominal schemas it was already ridiculous. Now if you look at this here, using this very, well, not very optimized implementation of a data log reasoner, you notice that the times don't really change if we introduce more nominal schemas. Now this is good. The things in brackets are the times using full grounding. Okay? Here we don't use full grounding. So the only thing we need to do is we need to find an efficient data log reasoner to actually do this, and then we have a good score. Let me skip this part and just make a last remark. That's essentially my last slide. A last remark on a different train which started with this. I mentioned earlier that it's kind of clear that these nominal schemas make a conceptual bridge between the description logic paradigm and the rules paradigm. And of course, in the description logic world, people were voicing for a couple of years already that sometimes you just need non-monotonic modeling aspects. Not only for closing the world sometimes, because if you kind of get your data from databases, then that's probably sometimes what you want to do. Okay? If the knowledge that if it's not in the database that that I'm a Turkish citizen, then I'm probably not a Turkish citizen. Okay? But with open world, it's very difficult to do that. And at the same time, doing something like default type of reasoning is something which at least modelers would like to have. So yes, trying to merge non-monotonic paradigms into the open world description logic paradigm is also a train of research, which I could have talked about here, but I decided to talk about Alden rules. Now once you have nominal schemas, you can think about, well, does this help? Does this help in integrating these paradigms? And just very high level. One thing which is relatively old already, 20 years I believe was when it started, was auto-epistemic description logics. Endowing description logic with auto-epistemic operators. Tonini, Rosati, Scherf, I believe as well, as a couple of people there in the 90s. So this is known. And what we can do now is we can just endow this description logic with nominal schemas, of course. Okay? I mean, we have the new description logic paradigm here with nominal schemas. And if we do that, then this actually results in a language which incorporates most of the major approaches to non-monotonic extensions of description logics. So it really captures a lot of them. In particular, it captures hybrid NK-NAP, which was developed by Boris Motig and Riccardo Rosati, which is a hybrid approach because it uses description logics together with rules, essentially 2 knowledge bases which are intertwined by sharing predicate and individual names. So we have that covered, and that means in turn the paradigm covers non-distributive answer set programming, or data log with stable model negation if you want. And it also covers DL programs. So this is the kind of DLD hex approach by Thomas Eiter, which you may be aware of, which is also a hybrid thing between answer set programming and description logic reasoning. Okay? So this essentially goes towards a unified logic for use in the semantic web. We still have to work some more on the decidability results because our decidability constraints look weird. Okay. We obviously also cover owls, Freud deep. We cover Etalog because we have our nominal schemas in the picture and so on. So Matthias would be a better. Matthias Knorr, he's in Lisbon, would be a better person to talk about. So conclusions. Paradigms are converging. That's good. Okay? If I look back to say 7-8 years ago, there was big rowing going on in the semantic web community, and why description logics, why not rules, and stuff like that. We now see that things are converging, okay, conceptually. That's a good thing. So that's helpful. And of course, there's more work needed. For example, regarding algorithmizations, regarding relating LDL and extension rules research. I think there's a lot to be done there. And about making non-monotonic reasoning fit for semantic web applications. That's actually, I think, the more interesting bit of the non-monotonic reasoning work. Not look for a big unifying logic, but trying to develop non-monotonic versions of description logics which give features to the modeler which they can actually understand. That is not that easy. Okay, that was what I wanted to say. Thank you very much, and if there's any questions, please let me know. What we can encode in description logic is transitivity of a predicate. So this is what we can express. Sorry, transitivity of a binary relation. So I do not know exactly how the relation here is, but I mean one thing which has to be taken into consideration is that we are severely restricted in the use of binary relations in the description logics. So I'm not sure where the kind of what the result is based and how it looks on the technical level. That you cannot represent it on the predicate logic side, but I guess it must be somewhere there.
But you can't express minimality.
You can't express
minimality.
Oh, you can't express minimality. Yeah. Oh, yeah. That's what we need for transitive closure. Oh, thanks, Michael. So you know more about this, of course. Very good point. You need to, for making the closure, you need to have minimality, which would be something like an induction axiom. And of course, this is in a sense a second order. We don't have that in description logic, but that's not a problem. Okay, we cannot talk about this type of minimality anyway. We're completely open world, so from that perspective, yes, we cannot model transitive closure. Correct. Thanks a lot, Mike.
So great talk.
Thank you.
Very good overview and synthesis of two fields. I have a graph structured knowledge base that you should try it as well.
Great, we should talk about that.
Yeah, and so the question I had for you was, is there any work on adding para-consistent features to description logics? Because in the current description logics, even if there is one inconsistency, you're hoped. You can't do anything.
Yes. The answer is yes. The other answer is, I believe, the most recent work there is actually by myself, so I could have talked about this. There have been very early attempts to looking at para-consistency. Already in the 90s, Peter Pavel-Schneider was one of the early people doing that. And then there were some developments throughout the years. And we have recently, I mean, para-consistency uses four-value logic for doing that, of course. What we've done, and the journal paper should actually come out in the final quarter this year on that, on para-consistent reasoning with OWL. So what we did was we carried it over to four-value logic. The key question is, how do you actually make the connectives for the four-value logic? Because you have several choices, of course, with some of them. You know, certain things break down in a para-consistent context. Like the standard way you can rewrite an implication into different forms, like with disjunction negation and so on. And depending on how you actually write it before you put it into the four-value context, they would usually look different, because these translations usually don't carry over to four-value logics. So what we did in that case was we actually looked at a practical angle here and said, let's use the type of translations which allow us to implement reasoning over the logic by transforming it back into classical description logic reasoning. And this is what we propose in this paper as the main variant. Of course, there's others around as well. So yes, there are para-consistent logics. I, however, have to say that I have a certain reservation regarding the use of para-consistent logic. I probably shouldn't say that because I wrote that paper and some others. And the main reservation I have is that I think the real problems we have in using semantic web data, big data, okay, for semantic web applications which use deduction in whatever form, is not logical inconsistency. Okay? That is certainly also something which comes into play naturally. One thing you can think of is you merge two knowledge bases, and through the merger you get an inconsistency. Then if you have a paraconsistent paradigm, well, it makes a lot of sense to have that. However, I believe the real problems are changes in perspective, how you express your knowledge. Slight changes in the way you conceptualize your notions, okay, between one knowledge base and the other. Design decisions you have made there. That becomes very apparent, for example, if you look at the geoscience as an application area, something I recently started doing, where it's even impossible to find a universal definition of, say, what a forest is. Okay? And that's not because it's a big scientific problem to do that. Okay? It's also a political problem, okay, to do that. So you have to live with different conceptualizations because they're just part of our reality. And this is not something which should be handled from the perspective of logical inconsistencies. Okay? The exact ways how to deal with this type of conceptual shift between knowledge bases, I believe nobody really knows how to do that. But these are, I think, the main issues we have to solve if we want to apply deductive methods to big data problems. So, but still, I mean, it's worth looking at this. Thanks a lot for the question.
I have a final one.
Right. So, I have some question about the last part of your talk. When you have this, so I don't know much about this autoepistemic description of the and so on, but there has been many work on integrating rules and ontologies at a certain point, like Rosati, DL plus log, and things like that. And at some point, I see there's no more discussion about that direction, and now you come up with something kind of reviving, but also maybe some new things here. So can you describe what is different between those that happened before and what you're doing now?
Right. Now, if you ask me personally, I think there's two research directions which are interesting. One is more interesting, one is less interesting. Okay. This is about the less interesting line, I think. This essentially is attempting to unify different logics. If you look back at the semantic web stack, then in all versions this keeps changing over the years, of course, right? As things are developed and perceptions change, so it's rather interesting to look at the history of this picture in these different installations. But essentially, almost since the beginning, there was always this box here, which says unifying logic, where nobody has an idea what this is supposed to be. The reason I believe why it's there is because it's a kind of reminder that different standards for representing knowledge on the semantic web should not diverge completely. They should somehow stay together. So, from my perspective, this is a conceptual piece. Okay, the question: can we keep these things still together? And the work which I've been talking about is essentially doing this. So it tries to make a bracket, a unified bracket, over many of these nomonotonic extensions. You mentioned some others by Rosati, DL plus log, and so on. And we have most of them covered. Okay. Now I don't think that's something which will lead to a practically usable logic. It's more making this conceptual bracket here. The more important question, I believe, is a different one. The more important question, I think, is the question how to actually make two features which are prominent in non-monotonic reasoning fit for use in ontology-based systems. And the two features are local world closure. So you don't want to completely close the whole world, you want to close parts of the world. This is called the local closed world assumption in this area. And the question here is, how do you do that in such a way that it's efficient? That's a problem, right? Very often these non-monotonic logics just go out of the roof in terms of complexity. How do you do it such that it's efficient? How do you do it such that it appeals to the intuition of the modeler or the user, okay? And that it does not become a very complicated semantics, which you usually have, right? I mean, who really understands kind of the different versions of world closure, if you look at circumscription, ultra-epistemic, or default logic, all of them have notions of world closure, right? Now try to explain to a non-logician what the difference is, okay? And before we're able to do that, I think it's going to be very difficult to actually use these logics. The second aspect is using default type of reasoning, not necessarily default logic, okay? But the reasoning with stereotype, the Tweety example which you know. And we may have to actually separate those two. They're usually looked at together. I don't see a conceptual reasoning, but these should actually be based on the same modeling paradigm, okay? Now I'm preaching to the priests probably here. So I think this is the important part. So how do we make this practical and implementable and useful and intuitive for the user? And I think there's many open questions here. There's some work in that direction. There's still some stuff missing, of course. Thanks a lot for the question. Yeah. Oh, I don't know if we're out of time.
So you mentioned that you find writing description logic expressions hard, and I agree with you. So, but are there people who actually can write description logic expressions without any problems? Maybe it's, I find it hard to write description logic expressions, and maybe it's my bias that I first was introduced to logic programming. But is it possible to actually write description logic?
Sure. I mean, I know even people who actually don't only do that. They actually write them directly in XML, which I think is not important. But yes, you can get used to that. And I mean, you can do it. But I just feel that I can focus more on the modeling aspect if I write a rule first. Okay, then I understand better what it is. Or I use some type of hybrid syntax, which I can do. I mean, instead of a unary predicate, I use a complex description logic expression and write that down if it seems to be more natural to me. So essentially, if I model this first on paper on the whiteboard, then I just use whatever means I have, and then I try to convert into the corresponding paradigm. Yeah, thanks. Okay, I guess we're out of time. So thanks a lot.